All right, I thought I'd put together a dependency injection demonstration for a friend of mine. However, I realized that before I do that, I should probably design this demonstration app, and this would be a good opportunity to show how I use DrawIO to create component diagrams and class diagrams so that we can kind of solve the problem of component boundaries before we get to coding. I think it saves a lot of time, and we can also evaluate the kind of architecture we want to implement. DrawIO is, I believe, a free app. Um, just take a peek at that. I believe, yeah, it's just draw.io. You can use this application online, or they have you can download it. I think it's available for download. I like running the local copy, just a little faster. And if you're working in a corporate environment, it's probably a little more secure to have everything stay local. There's trade-offs though. So I'm going to go ahead and create a new diagram. I'll make it blank. So what I'm attempting to do here is to create a UML diagram. So I don't, if you're not familiar with UML, it's a standard. Unified modeling language. What's cool about that is you've seen many different kinds of drawings that illustrate systems or software, but there's actually a standard definition of this language. So we're not, it's not like the Tower of Babel where we're all drawing different diagrams with different conventions. If we use the same visual language, we can all be speaking the same language and communicate a lot faster instead of going, hey, what does this box mean? As you can tell, UML has evolved quite a bit. I believe it's 2.0 is the current version of UML. There's different kinds of diagrams defined by UML. You've got class diagrams, component diagrams, uh, sequence diagrams are one I like to use a lot. I haven't used all of them, but they're all useful in different ways. A lot of times the different diagrams are illustrating, they're just different views of the same system. You're solving a different communication problem. For example, with component diagrams, you're illustrating, the domain of a chunk of code or a chunk of the system. And typically it's great for illustrating the dependencies that this one component might have on another. A class diagram kind of zooms in and it focuses on the relationship of the individual files within a software system. So, and then there's sequence diagrams are usually, they're good for tracking the calls between components or classes. So there is some ambiguity in the definition, and it's on those edges that things can get a little confusing. I'm not a UML expert, but I do try with each new diagram, or I try to get better at this, and I try to defer to what is the standard rather than making up my own conventions. So that said, I'm going to go ahead and create a component diagram of the software I'd like to build, and I'm probably going to bend some of the UML standards, not out of willingness, but out of ignorance. So if you catch me bending some of the rules, feel free to comment and let me know, and that's how I get better. So anyway, the first thing I'll do is I'll make sure that of the different tools that are available, it's the UML set of tools. There are many drawing tools out there. DrawIO is somewhat accessible. It's not perfect, but it gets the job done for most of what I need. So there's general for different drawing shapes here, or if you want to create a more informal flow chart, there's flow chart related items. And also, when you're working within an organization, your teams may land on certain visual standards that are kind of specific to your team. When in Rome, speak as the Romans do. Okay, so the first thing you're going to do is you're going to see an empty sheet like this. I like to go and deselect page view because pages are kind of worthless to me when I'm drawing. I kind of want that infinite canvas. So let's start by looking at components. Like this is your typical component. This usually means module or component. And when I say, probably the first thing that needs to be clarified amongst the team is what is a component? In software, I like to defer to Robert Martin's definition of a component, meaning that it's a unit of code that can be deployed independently from the rest without affecting the rest of the system. In other words, if you're coding in .NET, which is what my code sample is going to be written in, it's going to be a DLL. I think in Java it's going to be a jar file, but it's a unit of code, a file that gets compiled that can be deployed independently. So this is kind of your traditional icon that represents a component. I don't like how DrawIO scales this. This looks kind of ugly and it loses the visual indication of a component. So, however, there is another indicator here. It has the little component icon. It just says this is a component. And then this tends to be more flexible. This annotation is, I've heard it referred to as a stereotype. This is useful for being more specific about the kind of component. And then I like to name the component right here. I will play around with the sizes, and with a history in visual design, I do try to design these in a way that's visually appealing, because visual hierarchy does matter. You know, the way things are presented visually affects readability, and you really want to get to the meat of your message when you're designing something and sharing it. So let's get to it. So I want to build this kind of proof of concept that illustrates how we can use dependency injection to swap components. So really, I'm just looking for an excuse to illustrate how to use Microsoft's dependency injection libraries. There's many out there, and I just kind of want to demonstrate that. So the first thing I'm going to illustrate is, you know, we'll probably have some main component. What I mean by main is I'm going to create a console application, and I might even put, hey, this is console. Hopefully I spelled that right. And, you know, I could just kind of do your traditional down the stack, and these little arrows kind of show up dynamically. And I'm kind of finicky. I like to, you know, make the spacing reasonable, so I'll tighten it up as much as it makes sense. Well, the problem with components, when you see when you see arrows in a component diagram, this is illustrating dependency, not calls. It could coincidentally be that that arrow also represents the direction of call. Like the main could call some second tier thing. Let's call this our business rules. And over here, this is our data access, right? So this might be your presentation tier or your UI. In a console app, it's just your main application that kicks things off. The console is the presentation tier. So the problem with this kind of architecture is the thing that is the most important in the world is the thing that has no dependencies. And what that means is you could change this code or this code, and this code would not be affected. However, if you changed this code, the data access, the business rules would be affected. And additionally, if the business rules were changed, then the main code would be affected. Now, you're going to always have dependencies in software. The real trick is figuring out which component should depend on what. Well, traditionally, the database has always been considered the most important thing in the world. A lot of developers will start when they're building a system to design the database, the tables, they'll think about the relationships, and then they build the data access layer with all the CRUD, all operations. Maybe you start using Entity Framework, and then you kind of build the business rules around that. But there's a problem there because the database really should be considered a detail. In the real world, once, you might start off using Oracle, and then the company might want to swap to use SQL Server, or maybe you want to swap to use MongoDB, or maybe you want a system that uses an assortment of data access. The data and the data access should be considered a swappable detail. So we want to consider the business rules to be the most important thing. And a good analogy for that is, imagine there are no computers, and you're in the business of, well, let's use this example I'm going to build. I'm building a recruiting application. So my application is going to recruit people from school and turn them into employees. Well, I want to be able to swap, maybe I don't always want to get recruits from school. Maybe I want to get the recruits from a boot camp. So I should be able to swap where I get the employees from and still be able to have this uniform concept of recruitment. Now, if you take away computers and you take away software, you can still do the X of recruiting. You could have a recruiter, maybe from the human resources department, and they go visit the school and they reach out and communicate with the students. And they write down their information and their phone number, and they track them, and maybe there's a workflow that once the student graduates, they're eligible to become a student. Maybe there's a process for internship. If computers aren't involved, that process still exists, and that process is what they call the business rules. So the business rules are the most important thing in the world. The database is just a detail. So I'm going to illustrate that right here. So I'm going to create a recruiter. The things that are the most important in the world, those are policy components, because that's your company's policy. The things that are not the most important, those are detail components. So just to kind of make my point, the problem is if the recruiter component is the most important, it still has a dependency on data access. That means if data access were to change, then recruiter would have to change, and we don't want to change it because this is the business rules, and business rules shouldn't change. We shouldn't change how a business operates because of a software detail. In this case, the data access, we'll say it's a school. Maybe somewhere over here, we've got an alternative component, and we'll call it a boot camp. So already we've got a problem, because if the recruiter wants to use a boot camp, well, it's going to have to rewrite part of its code to move that arrow over here. So what we want to do is we want to invert this arrow. So one way you can do it is have the arrows point up. So now school is a plugin that implements the process of recruitment. So it's at this level, as we're designing the components, we're identifying which component is the most important in our system, and we're identifying the relationship of the different components. So in this scenario, school is a detail of recruiter. It depends on the recruiter. The school doesn't have any purpose in the system without recruitment. Recruitment stays the same whether or not school comes or goes. Maybe school is replaced with boot camp. And this system would still work. The recruiter business logic would stay the same. What if instead of using a console application, we wanted to swap that and use, instead, let's say, what if it's a web application? Or what if it's a, what if it's a mobile application? Regardless of the user interface, the business rules should stay the same, and we should be sure to decouple the presentation from the business rules. Now, obviously, systems tend to be more complicated than this. This is an oversimplified system. It looks very familiar. A lot of developers first start by learning this concept of a three-tier architecture, and you could sort of relate that here. So I'll go ahead and delete these for the purpose of our demonstration. I want to just have, in fact, I'm not even going to use school. I'm just going to, or boot camp, I'm just going to use school. So when I develop Recruiter, I would like to be able to write a unit test and use test-driven development. And school is a detail that doesn't exist while I'm unit testing. So I should be able to mock out this thing that the school accesses. So so that's going to be it. That's my component diagram. You know, one thing that's nice about DrawIO is you can add a little color to it and it looks nice. And but that's all good, except if you try to hand this off to, let's say, a junior developer who's not familiar with dependency arrows in a component diagram, and they're like, I just want to code. Why can't, hey Steve, why can't I just make a call to the database directly? I don't need this business rules. I can just have main, have a bunch of if statements and just get the student and put them to work, and I can just get around it. Or maybe we say main, get the student and then send them to the recruiter, and now main is controlling the flow. Well, in that case, in that scenario, main would become the most important thing in the world. And main, if it contained the business rules, if we swapped main for a web application, then we lose all those business rules, and it requires a very expensive amount of coding. So, oh, that didn't display correctly. Let me fix that. Now, the thing is if main is calling recruiter and school is plugging into recruiter, well, let me take a step back. You can't have two main. You can't have two simultaneous callers. Like, where would the flow start? That's not what's actually happening. The flow truly starts in main. It goes down to the recruiter. The recruiter executes some business rules, and then it's going to get the student from school and turn them into a recruit. They're not actually, school is not actually calling recruiter. This arrow is a dependency arrow. So a junior developer might look at this and go, what is a dependency arrow? How is that different? Well, what's really happening is you have dependency inversion going on in here, and there is a concrete class inside of school that implements an interface that is owned by the recruiter. I'll make another video to talk about dependency inversion principle, but I'll go ahead and illustrate it here. So what I've been finding is useful is to also deliver a class diagram. So let's take this. Let's take this component, and this is where I start to get liberal with the UML convention. I'll just kind of move this this name sort of out of the way, or maybe I'll keep it centered. But now I want to really expand this component because the concept of component is still the same. But this component is going to have classes inside of it. So this, what I start to do is a bit of a hybrid between a class diagram and a component diagram. Remember, components are individually deployable units of code, but class, it's the components inside those components. So let's look for, I kind of like this convention. So we might have some, let's call this interface, we'll call it recruiter. I'll kind of stretch this out a little bit so it's easier to read. And one thing that's a little awkward is I could move these inside of here. And if I do, when I start stretching this out, these things change sizes and it kind of annoys me. And that's a limitation of DrawIO. So I tend to just shape up my classes first and then drag them all inside of the component later. So we might have this recruiter manager, or it could be a factory, or it could just be a regular recruiter class. It's not really important what you call it. Well, I guess it is, because it depends, you know, if it's a factory, you should call it a factory. If it's an adapter, you should call it an adapter. In this case, you're managing recruits through this interface. So, well, you're going to have this interface, and it's going to be implemented by something concrete. And I like these stereotypes because I like to be explicit about what the thing is. So, well, this is a concrete class, and it's going to implement this. Now, typically in UML, you're going to use a dotted line for implementation. So here you'll see that this recruiter manager is going to implement the iRecruiter manager interface. So if there's a method like recruit, then this is the contract that promises the calling code that there's going to be a method called recruit, and recruit manager is going to implement that. If I were doing a full-blown class diagram, I could get even more detailed, and I could put the actual method in here and the field type. So maybe, you know, there's a, and I can be more detailed like that. So how detailed you get depends on your audience. For component diagrams, I'm showing the relationship of the classes as they act as the plumbing for my components. You might have a technical lead or a lead developer take over, and they would do the very meticulous defining of all of the interfaces and what it means to be a recruiter manager. But for the components, its purpose is to see the plumbing and how the components actually talk to each other. So, all right, so we've got this recruiter manager, and let's see. It is going to, well, recruiter's going to reach out to some source like school. And except we don't want to call it school, because school is sort of, it's more of a employee source. And for lack of a better name, I'm going to just call it, employee pool. And this is an interface. And the reason it's an interface is the recruiter manager doesn't know how it's going to get those employees. It just knows that it needs an employee pool, and it can trust that if it calls this interface, it's going to get the employee that it needs. So, and what's the employee pool going to get you? Well, it could get you a going to get you a recruit. And this isn't going to so much be an interface as it is a model. So a model is kind of like a POCO, plain old common language runtime object. I think they call them different things in different languages, but it's basically a class with no business really going on. It's not a business object. It's just, it's a class that's used to transport data. So recruiter manager is going to call the employee pool interface so that it can retrieve a recruit. And one thing I like to do here is make the lines a little stylized. So, and this is where you can take liberties with your design. So the thing is whoever calls this recruit manager, they're not looking for recruits, they're looking for employees. So the recruit manager is going to output employees. And I'm making this decision right now, so. So what we've got going on here is this recruiter manager, it's going to call an employee pool that's going to generate a recruit. The recruiter manager depends on this recruit coming back, so it has a dependency there. And the recruiter manager is going to do some mapping, and it's going to convert that recruit into an employee. And I should make that singular. And then this interface, whoever calls this interface is not going to know the magic of the business rules. It's just going to see an interface, and it's going to expect from this interface to get an employee as a result. So now we've got this nice definition of what it means to be a recruiter component. So we can kind of, whoops. Maybe I'll, this is where I play around with DrawIO to get it to behave. Get it to size. And this is very subjective. Maybe you're not as finicky as me, but I think having a nice presentation really helps with the consumption of that information. So now this component is kind of exploded, and you can see at least the main bits of the recruiter. There might be other classes within this component, but we kind of don't care because these components represent the boundaries of this. Sorry, these classes represent the boundary of this recruiter component. So if you have this thing called main up here, it's going to make a call, and let's get that into the picture, right? So we'll do an explosion of main. I'm calling it a detail because that can be swapped with anything else. And inside of main, there might be some, we'll just call it program. This is if you create a standard console app, you get the program class for free, and it has a method called main, and it's the thing that gets executed. You could add other layers within this main tier to represent an application or whatever, but we're going to keep this kind of simple. And this is where I like to size things up. And now program is going to make calls to this interface. So remember, program doesn't know about concrete. Program just executes and calls the recruiter manager, and it's going to trust that recruiter manager is going to return the employee. So we could then generate a list of employees and present that to the screen. Maybe there's some method that says recruit employees, and it's called through this interface, and it returns a list of employees, and then the presentation may want to list out all the employees onto the screen. And I'll end up writing that code in the next video to demonstrate all this. But again, the purpose of this video is to show how I can make these design decisions using a drawing tool before I write a single line of code. Now, the thing about architecture is there's probably an unlimited number of ways to design a thing. You're just making decisions here, and you're evaluating the different trade-offs for those decisions. I could very easily have just made a single DLL that does all the things. And the trade-offs would be, well, the pro would be I could get this done a lot quicker with a lot less code. The cons are the code wouldn't be very maintainable, because once I have to start swapping or refactoring, then that becomes very expensive. If you've worked in any kind of professional environment, so many times the code, as it goes through iteration after iteration, it gets more and more unmanageable, and that can get very expensive to a company. So, all right, so let's illustrate this school component now, and let's get that in there. I'm not really going to draw the swappability. I'm just kind of drawing that first state of the application. So I like to align this at the top. And so now we need a thing that actually implements this employee pool. And I'll just kind of throw this over to the side for a moment. And maybe school has an employee pool, and it's going to implement this guy. So again, we use dotted lines for implementation, and it's going to return these recruits. And this employee pool is going to do some magic. In fact, I'm just going to call it well, let me see. I'm creating a student model because the school component, it knows about students, and we'll turn this into a reference. So make that a solid line. So the student manager is going to, actually let's turn this into a solid line also. Okay, so the employee pool gets called, and it's going to say, okay, I need some students, and I'm going to turn them into recruits. So it's also going to reference that student, and it's going to, employee pool is going to call the student manager to retrieve some students. Then it's going to take those students and convert it into a list of recruits. Now there's some problems with this design, but that's out of scope of what I'm illustrating here. Get my stuff lined up. You can tell I'm very picky about presentation. So there you can see now those child objects have decided to stretch out. And that's one of the shortcomings of using DrawIO. Maybe next time I'll use some of the other drawing tools, and we can kind of evaluate which ones we like better. Okay, so add a little space between here. Cool. So let's look at what's going on here. This is the same drawing as this. Main depends on recruiter, and school depends on recruiter. And here's why. If you look at the class level, well, we've got this program. It's going to call this iRecruiter Manager, and that iRecruiter Manager is going to be implemented by something concrete called Recruiter Manager. And once it's called, it's going to return this employee. But to get those employees, it's going to call an employee pool, and that employee pool is going to return recruits, and it's going to map those recruits into employees. You know, I think I'm going to call this a recruit pool. I think that would be nicer. Now, notice I don't need to change the name of employee pool as long as employee pool implements recruit pool. In fact, I might call this student pool. And yes, so we'll, just for the sake of illustration, the names of the classes should be a name that means something to the component in which it lives. If it just happens to implement an interface across the boundary, well, that's a detail of the implementation. So, okay, so we've got this recruiter manager. It's going to call some sort of recruit pool to get a list of recruits, and it's going to map that list of recruits into a list of employees and return it up to the program. Well, it just so happens that this school component is implementing this recruit pool. And anytime you have a component implementing an interface across the boundary, well, that basically makes this a plugin. So it's a special kind of dependency arrow, right? Notice that all the arrows are going up, so this arrow is still true, but it's really a plugin. So one thing I like to do is, rather than use this arrow, because that arrow confuses people and makes it look like a call, is there's this icon here. They call them lollipops. And again, DrawIO is a little finicky. Sometimes it's referred to as a ball and socket. And now this looks like a proper plugin. The lollipop is plugging into the socket. So that cup is sort of representing this expected interface. It says, I expect somebody to fill this interface so that I can implement it and do the things I need to do. And as long as there is a lollipop that fits in here, I don't care if you're a school or a boot camp or someone off the street, as long as you can follow the interface that I'm expecting, then I can execute my business rules without compromising my business rules based on this detail. So this drawing is just as valid as this drawing, but this drawing uses classes to illustrate the plumbing. And it's really a magnifying glass on that dependency inversion. And this is, they call it dependency inversion because instead of the arrow going down and that interface living down here, all we did was move the interface up here and that arrow got inverted. It's now pointing up. And because it's pointing up, we can illustrate it as a plugin. So I'll go ahead and save this, and this will be the thing I want to build. In my next video, I'm going to actually build this out and show how I can create a unit test that will mock out this recruit pool with a mock recruit pool. And once this is developed, at runtime, we want to be able to replace that mock with something tangible or concrete, a concrete plugin called school. And well, somebody's going to have to own the dependency injection. And usually that's done in main. So what you would end up seeing is whoever's doing dependency injection would also have a dependency arrow over here, but we won't illustrate that yet. All right, one more detail. One thing that's really cool about DrawIO is I can select the part of the drawing and I want to export this as an image so I can put it in my documentation. So there's a file, export as, I like to save it as PNG. And here you can do selection only. And I think it's more classy if you add a little bit of a border. 10 pixels seems to be nice. And I can hit export, and it's going to ask me where I want to save the file. So I can save this as a component diagram, and I can save this as a class diagram. Now, as I said at the beginning of this video, I'm edging towards following UML standards, but I think that this is still not 100% UML standards. This is me blending or creating a hybrid of class diagrams and component diagrams, because a junior developer is going to get confused when they look at this if they haven't yet learned UML. So I would recommend getting your team to learn UML and speak the same language, but until you do, do whatever it takes to communicate your design strategy. All right, so there we go. All right, there's one more thing I forgot. So of course, as soon as I saved the image, I realized I had a whole lot of mistakes in it. And that underscores a really important detail about these diagrams. Is as important as any code review or pull request on actual code, if not more important, we should be reviewing the diagrams. In fact, there is a process for that in most companies. They call that RFC, request for comment. And the idea is that you should get several eyes on the design so you can catch stupid mistakes like this. So of course I took a look at it and I saw, well, I really messed up. This is not an interface, neither is this. Also, I didn't code to an interface here. So let's take a look at the diagram and make a couple fixes real quick. So after I did a pull request or created an RFC for other designers or architects to look at this, they go, hey, that's Steve, that's not an interface, that's concrete. And furthermore, this isn't an interface. It's not, nothing's being implemented. So it really is a concrete manager. Now, of course, we could have an interface here and the student manager could implement that interface, and maybe it should because that's what enables unit testing, but that's out of scope of this diagram. So, you know, once again, you see the dotted line is implements or indicates that a concrete class is implementing an interface. So student pool would be implementing iRecruit pool, and it would be returning the recruit model. So, all right, thanks again.